Right, so a good milestone here. The student has spent a lot of time on this, and what he's got is he's got a one-to-one mapping from the pins on this real board into the simulator, and he's going to show us that, if he would be so kind.
Yeah. So this is our circuit, which is same as the circuit we have on this board, and the names I have tried to keep the same. So this is the transistor T1, T2, T3. So I will also explain how the circuits work. First we start from the transistor T1. So we have these two inductors which we made here, that is L1, L2, and how we have coupled it on the multisim, that we have, this is our inductor L1, this is our inductor L2, and we have used this inductor coupling which is available in the transformers, and we have placed these inductor L1 and L2, and we have set the coefficient to 0.9, so it shows that how good they are coupled with each other. And to show the presence of a metal, I have placed this resistor in this part of the LC tank circuit. So when I will increase the resistance, it will show that a metal is near the surface, so the inductance will decrease and the voltage levels will decrease. So first we will just do the transient analysis to see that what is the voltage level we have at this T1 and how much that voltage is being given at the base of the transistor T1. So this red line, that is the voltage we have at transistor collector, and the green is the voltage we have at the base. So we can see that at the collector, the DC level, as we know that we punched it to 3.9 volts, so it starts from 3.9, it goes up till 6, and it goes up till 2. Although we have a voltage of 3.9 volts, but it is going till 6 because the DC level is 6, so when the polarity is opposite, it goes till around 6.7 volts. And this green, it shows the voltage which is at the base. And if we zoom in, we see that when the voltage at the collector it is increasing, the voltage at the base is decreasing. And the same, if we can connect the oscilloscopes to the circuit, then it shows it has the same effect. And now if I go ahead, then I have completely mapped the circuit, and there we have the LED which we have on our board as well. So when we do it in the interactive mode and run the circuit, so now this LED is off. And when we see that when we were tuning the circuit, so when we increase the resistance, there was a time when the LED turned on. So I increase it and we see that this LED turns on. And why it turns on is because at the base of this transistor, which is this transistor, is acting as a switch.
And that's the tuning knob on there.
Yeah, that is the tuning knob right here.
Gotcha.
So when we increase this resistance, basically the oscillation of this tank circuit stops. So when this oscillation circuit stops, so this transistor 2, it is turned off. So we have the voltage at the base, it becomes 2.6 volts, so this transistor turns on. And if I will reduce this resistance, so we see that now the LED is off. Why it is off? Because this transistor is off. And why it is off? Because the voltage at the base is less, so it cannot be forward biased. So now I turn it on again, and now I will reduce this resistance. So this resistance will show that an inductor is nearby. So when I will increase the resistance, so the LED turns on.
Yeah, got it.
So this is the whole mechanism of the metal detector.
Fantastic. Can you show us the on your phone, because you've got the same representations, but in the real world that you've done on the oscilloscope, haven't you? So what's this one?
This is the voltage which is at the collector. So see that when we are increasing the resistance, the voltage, the oscillation, they die down.
Yep, gotcha.
And another one I would like to show you. Yeah. So again, if you can see this video, the green one is the voltage at the collector, and the yellow one is voltage at the base. We can see that they are out of phase.
You can even see the turn off on the transistor. The patches up there as well. Yeah, nice. So did you suss out what frequency?
Yeah, it is 97 kilohertz. Yeah, we can see the frequency.
And you can do the maths to prove that with the.
Yeah, I can do that. And I have tried to actually, because I could not make the inductance, so I saw that how much value is on the oscilloscope. So it was around, it was there. So I tried to use the values of 3 millihenry. So now it also creates the same frequency.
Nice. Did you have to use any startup conditions?
No startup conditions.
That's a major achievement. I've not seen one without startup conditions or without cutting the circuit in half.
That's
So
a complete. I fear that
you're the first one to
addition
have
of
done this as a complete circuit rather than in its constituent parts.
The addition of this resistor here was key to you getting that working properly.
It depicts the presence of a metal.
Very good job.
Well done.
Thank you.
Pleased with yourself?
Yeah, thank you so much.